Alrighty, 8.4, adding and subtracting radical expressions. So, adding and subtracting radicals is incredibly simple when they match, okay? So if the only time we can add and subtract radicals is when the radical itself actually matches. So it has to have the same index and the same radicand, okay? Other than that, you really can't add them together. So it makes life really easy when it comes to adding and subtracting, because a lot of the time the answer is I can't. It's very almost identical to the way we add like terms and polynomials. So if you recall, we had 2x plus 3x, right? You can combine that using the distribution property. I can say, okay, these are like terms, so I can take out the x part, and I end up getting 5x. In other words, you add the coefficients, right? I can't do that with something like 2x squared plus 3x because I can't take the x part out, right? There's too many x's there. So can't do with that. It's the same exact logic with radicals. So if you look over here, these two guys have the same radical, the same root 3, right? Square root of 3. Because of that, I can use distribution property, take it out, and I end up adding the coefficients in front. I get 4 plus 2, so 6 root 3. In other words, I have 4 root 3's and 2 root 3's. Together I have 6 root 3's. Same goes for subtraction. Just pull it out, right? So 2 plus negative 5, negative 3 root 3. Only works if you have the same radical. The same radical with the same index. Alright, let's try a few out. Add or subtract if possible, simplify first if necessary. Just because they don't look identical doesn't mean you can't add them together eventually. You have to use your simplification rules. Okay, so let's use our simplification rules. Let's reduce both of these. 3 root 24. Let's start with that one. That's the same thing as 3, well, let's divide it up. So that would be 8 and 3, and 2 and 4, and 2 and 2. Okay, so that would be 2 times 2 times 2. So this is going to be the same thing as 3. 2 times 2 times 2 times 3. I see a group of 2's here, so 3 times 2 squared, 2 times 3, right? Or 3 times 2, root 2 times 3. So I took that squared part out, right? In other words, I use that n canceling property, and I end up with 6 root 6. So 3 root 24 is the same thing as 6 root 6. It's in simplest form now. Let's do the same thing for 54. Square root of 54. Well, I can break that down into, let's see, 54 is 6 and 9, right? So 2 and 3, 3 and 3. So 2 times 3 times 3 times 3. Really? There we go. Okay, cool. That's equal to, let's see, I've got a pair there. I'm still dealing with pairs because it's square roots, right? Square roots. And let's do, so we can rewrite that as 2 times 3 times 3 squared. The 3 part gets to come out, so it's 3 root 6. Now I see that I can add them because they have the exact same radical, right? They have the same radical. So it would be 6 root 6 plus 3 root 6. That ends up equaling 9 root 6. So I can add them once I make the radicals the same. 9 root 6. Let's try it again with some variables. Now in this case I've specified that x is greater than 0, so that way we don't have any negatives under the radical, right? So if that's not there, just make sure you make that comment, right? So x must be greater than 0. But let's try reducing these two. Square root of 20, so I have 2 root 20x minus, oh sorry, not minus, that's going to become 2 root, let's see, that's 2 and 10, or 2 times 2 times 5. So in other words, That's going to be a pair that gets to come out, so 2 times 2 root 5 or 4 root 5. Okay, so that first one's 4 root 5. Now we'll do the square root of 45. Let's see, that would be 5 and 9. So 3 and 3 and 5, right? 9 and 5. That becomes, 3 goes on the outside, 3 root 5. Alright, so I'm going to totally just drop my x's. My apologies. There's still an x here. There's no pair to take out. Still an x here, no pair to take out. Still an x here, no pair to take out. Same logic down here, 45x, x, and x. And again, no pair to take out, so I just leave it under the radical. Now, finally, I have 4 root 5x minus 3 root 5x. Because those radicals are absolutely identical, that becomes just a 1 root 5x. And we have our answer. Okay? So you can reduce as long as those radicals match exactly. They're welcome to have the same variables, or they're welcome to have variables, they just have to have the exact same variables, right? Same thing as like terms. Let's do one more. Okay. Whoops. Sorry about that. I have 2 root 3. Well, 3 is a prime. That's as much as I can get. 4 root 5. 5 is also a prime. That's as far as I can go. So these two I can't actually combine. This is the simplest form of this subtraction problem. 2 root 3 minus 4 root 5. And that would just be our answer. It's not no solution. Okay, it's not no solution. There is a solution. That is the solution. It's just you can't reduce it anymore. Okay, you can't add or subtract. Alrighty. It is very important to note that product rule does not apply here. Okay, it is not product rule. Just because I have this doesn't mean I can put them under one radical and do 3 minus 5. Okay? Addition and subtraction is not a product. It's not a multiplication. There is no product rule here. Okay? You cannot do that. So and just to prove it to you, the square root of 9 plus 16, the square root of 9 plus 16 is 25, which is 5. The square root of 9 plus the square root of 16 is 3 plus 4, which is 7, and obviously 5 does not equal 7. Okay? So that's just a little proof that this product rule does not apply. This is what we call a counterexample. If you find something that doesn't work for one of them, it doesn't work for any of them. Okay, so you cannot use the product rule ideas for this adding and subtracting. Okay, it only applies to multiplication and division. Right, that would be called the quotient rule, though. All right, let's add and subtract these radicals of higher powers. Let's do some higher powers. Once again, the higher powers mimic exactly, right? The same rules that apply for squareds apply for nth powers. Higher you go, the same it is, right? Big numbers are just big. So let's simplify these guys, because right now we can't subtract. They're not the same. Doesn't mean they won't eventually be. 2 cubed root of 16. That's going to break into 4 and 4, and 2 and 2 and 2. So 2 times the cubed root of 2 times 2 times 2 times 2 times 2. I see one pair of 3s. Careful, I am not working in squared anymore, right? Just because you see a 16 doesn't mean it's automatically a square root, right? It's not going to be 4. It's going to be a pair of 3s. So this is going to be a 2 on the outside and another cubed 2 on the inside. So we get 4 cubed root of 2 as our first number. Whoops, don't want to box that. The second part is 5, is it cubed? Yeah. Cubed root of 54. Remember, I can only add identical index, right? So I had to make sure that was still a cube. And that's 5 times, let's see, 6 and 9. That would be 2 and 2 and 3, not 2 and 2. 2 and 3, 3 and 3. And I'm looking for a group of 3. There we go, there's a group of 3 right there. So I still have that 5 on the outside. And now I have a 3, and the 2 is left over in the cubed root. So I end up with 15 cubed root of 2. And oh good, now they match. So now I can actually subtract them. So 4 cubed root of 2 minus 15 cubed root of 2, right? I'll treat those like coefficients. They are coefficients. They're the thing in front. So I will subtract those guys. I get negative 9 cubed root of 2. And that is my final answer. Negative 9 cubed root of 2. Awesome. Let's try one with the variables now. Same dealio. Same deal. Okay. So 2 cubed root of x squared plus y, or times y. Watch out, that is not 2q cubed, right? That's not 2 cubed, that's the cubed root. Just be careful of that. Sometimes writing math on a computer, that ends up happening. If you're ever confused on a test, come ask me, I'll tell you what it's supposed to be, okay? So I have 2 times the cubed root of x squared y. Well, that one I can't do much. I could change it to a rational, right? I could change it to a rational. That would be 2 to the x, or 2 times x to the 2/3, y to the 1/3. Doesn't really help me though, right? Because I don't have groups of 3 to take out. So I'm just going to leave that one as it is. I'm going to leave that one as it is. No groups of 3 to pull out. So let's try the other one. The cubed root of 8 x to the 5th, y to the 4th. Well, that one looks good because I have an 8. The cubed root of 8 is 2. Cubed root of 8 is 2. That's good. I have 5 x's. I can take out one group of 3. What's left over is 2 more, right? And then I have 4. I can take out one group of 3. What's left over is 1. So I get x squared y. Oh, and good. Now it matches. That's not a guarantee, right? But now the radical parts match. And I'm so sorry, this is still the cubed root. Cubed root of x squared y. So let's go ahead and subtract these two guys now. I have 2 cubed root of x squared y minus 2 xy cubed root of 2 x squared y. Alright, I will apply that distribution property, which says I can take both of these guys out. I have 2 minus 2xy times the cubed root of x squared y. Now, this is kind of a new part for us because we're not used to things being unalike when we take them out. Up until today, we've only taken out numbers, right? You only add the coefficients. But these are actually unlike terms, so I cannot combine them. I cannot combine them. The only other thing I can maybe do is take that 2 out. I get 2 times 1 minus xy square root of x squared y. But that would probably be as low as this could be reduced. And that's okay. That's okay, right? It doesn't have to look like anything. It's just I don't want to use improper rules to make it look like something, right? So if this was an answer or this was an answer, in my book, either one is okay because it depends on what you're going for, right? It depends on what you want it to look like. Actually, no, I take that back. It doesn't matter what it looks like. It matters that it's simplified. Simplified. Alrighty, let's keep going. Let's try another one. I can reduce this guy, I can reduce that guy. So let's try 5 root 4 to the cubed. Well, the square root of 4 is 2. I have 5 times 2, and I can make one group of 2, and what's left over is an x. So I have 10x root x. The other one, see, I've got 3 cubed root of 64x to the 4th. Okay, the cubed root of 64 is going to be a 4. Cubed root of, well, hold on. Because I also have an group of 3 x's I could take out. And what left over would be an x, cubed root of x. And I end up with 12x cubed root of x. Which is great, except for the fact that that's as far as I can go. Why is that as far as I can go? Their indices do not match. They are not the same. So the simplest form of this would be 10x square root of x minus 12x cubed root of x. Since those are not the same, that would be my finalist, or my simplified form. Okay. And again, that's okay. But you must simplify first. You must double check. Otherwise, there's no point. And regardless, you should simplify them regardless. Simplifying makes everything easier. 12x root x, or 12x cubed root of x is much easier to deal with than the 3 times the third root of 64 x to the third, or x to the fourth, right? So always simplify, even if the indices don't match. But if the indices don't match, you already know that you're not going to be able to subtract those. Let's do another one. This one involves quotients. Okay, so we got some quotients here. They look very different, right? One has a giant quotient, has a fraction under one radical. The other one has 2 radicals within a fraction. But we know those are the same thing, right? By quotient rule, we know those are the same thing. So let's reduce one at a time. I think I'm going to put them both into the 2 radical form. I'm going to put them both in the 2 radical form. Yeah. So I have 2. So this is the first one. I have 2 square root of 75 over 16. That's going to be 2 times square root of 75 over square root of 16, right? Square root of 75 is not a whole number, but that doesn't mean I can't reduce it, right? 75 divided by 5 is 15. I can take out, so that's square root of 5 times 3. Here's that 2. Square root of 16 is 4. So I get 2 times 5 root, oh darn it, root 3 over 4. Sorry guys, this little blue bar on the side you see here, if I touch that, it takes me to the next stop. It's sort of being helpful, but I can't get rid of it. I can get rid of it a little bit. That's cool. Anyways, alrighty, so now I have this guy, right? And I can simplify just a little bit to 10 over 4, and I can reduce that part of the fraction to 5 over 2 root 3. 5 over 2 root 3. Alrighty, let's try the other one now. I have 4, do that in another color. I'm sick of pink and green, let's do blue. 4 times root 8 over root, what is that, 27 or 72? 32. 32. Well, root 8, again, I'm not dealing with a cube here, I'm dealing with a square. It's very important to look at your indices. If you are so used to saying the cubed root of 8 is 2, the cubed root of 8 is 2, you might accidentally write that the squared root of 8 is 2. That's not true, right? The square root of 4 is true. So watch out for your index, right? Watch out for that index. Here, I can reduce it though. I can take out one of the 2's because I've got 2 times 2 times 2, so this becomes 2 root 2 over. Here I've got 5 2's, 32 is 2 to the 5th, and so I can take out 2 groups. That would be 4 root 2. And now I've got a root 2 over root 2. Those 2 end up canceling. So do the 4's. I end up with 2. So my final answer would be the green and the blue. 5 halves, root 3, plus 2. And that is as simple as I can go because one has a root 3 and one doesn't. Alrighty. Last one, let's try this one. Some variables thrown in there. Okay, cubed roots this time, but again, that quotient rule applies to anything. So I can take these guys, I can make them into each their own radical and see if they simplify. So I have 10 cubed root of 5 over x to the 6th is the same thing as 10 cubed root of 5 over cubed root of x to the 6th. The top one doesn't look like it cancels very much, and that's okay. So 10 cubed root of 5. But I have 6 x's, of which I need to make groups of 3, so I end up making 2 groups of 3, right? That cancels twice. Okay, that was the first one. Let's do the second one. Is 3 cubed root of 4 over x to the 9th. 3 cubed root of 4 over x to the 9th. Once again, be careful. We are now talking about a cubed root, not a squared root. So that top one, when I rewrite it, is not going to simplify to 2. It's not going to simplify to 2 because it's a cubed root, right? In other words, what cubed is for, that ain't going to be 2. However, we'll keep it like that. No, we can't. Yes, we can. Can we? I've got 2 and 2. I don't have any groups of 3. Never mind, it'll stay like that. But on the bottom, I've got 9, x to the 9th. I'm looking for groups of 3, so that makes x cubed. right? All right, and then my final answer doesn't look like it simplifies much. 10 to the cubed root of 5 over x squared minus 3 to the cubed root of 4 over x cubed. I got unlike terms, I got unlike terms, I got coefficients that I can't add. So that's my, final answer. Hopefully that cleared up some stuff about addition and subtraction of polynomials. This was a very short video compared to the other ones. But if you're still confused, feel free to email me. I'll see you in the next one.